4.1 Graphs of the sine and cosine functions. There are many things in daily life that repeat with a predictable pattern, such as weather, tides, and hours of daylight. They're periodic. So when you graph a trigonometric function, these graphs also have a predictable pattern. Therefore, they can be called periodic functions. You'll need to know how to graph all 6 parent functions, and we'll use our unit circle values to help us with these. Once we can graph the parent functions, then we can manipulate them by changing the period, amplitude, phase shift, and etc. So the first parent function that we're going to talk about is the sine function. If you'll remember, this is the unit circle. Let me see if you can see what I'm pointing out. Let me draw it out. Okay, so this right here is the unit circle. And the values that we put on the unit circle are what we are going to use to graph our sine wave, or our sine curve. Let me see. Let me make this a little thicker. Okay, so the way that we do that is, first of all, if you'll remember, sine is y over r, and in the unit circle, our r, or our radius, is 1. So anything over 1 is just itself. So sine, our sine values are going to be the y values from our unit circle. So on our first mark on our unit circle, where we have 0, where our y value is 0, on 0 degrees or 0 radians, that would be 0, 0. So on our sine graph, that's where we would put our first mark, is at 0, 0. And then at 30 degrees, or at pi over 6, this right here, our sine value, or our y value, is 1/2. So that's what we would put on our sine curve. And then they don't have it marked on this graph, but we know that at 45 degrees or at pi over 4, we know that that value is square root of 2 over 2. So that's what we would put on our sine curve, is the square root of 2 over 2, because that's our y value. And then at 60 degrees or at pi over 3, so this was the pi over 4, or the 45 degrees was the square root of 2 over 2. And then at pi over 3, or at 60 degrees, we have our value is square root of 3 over 2. So that's what we would put here. The y value is square root of 3 over 2. And then at 90 degrees, or at pi over 2, our y value is 1. So we go up to 1 right here on our graph. And then, of course, as we go around the circle, we have the values that go around. So that's what creates our curve here until we get back to 0. And then as we go around the circle, of course, our y values begin to get negative. All right, so we have these negative values until we get to -1. So that's why that's why our curve goes below the x-axis, is because we have these negative values until we get down to -1, and then they start getting smaller, and we go back up to 0. So they start getting smaller and go back up to 0. So essentially, it's as if we took this circle and just opened it up, unrolled it. And this is what we're putting on our graph, is the y values, and that's what creates our sine curve. So let's draw it out separately on this graph. So this, our y-axis is going to be our radius. So if I say that this is 1/2, let me make this a little smaller again. Okay, so if we say that this is 1/2, and this is +1, -1/2, -1. And then we'll have our quadrantal values. So this would be pi over 2, this would be pi, this is 3 pi over 2, and this is 2 pi. Of course, this here in the middle is 0, and then this will be our negative values. So if you'll notice on our sine curve, it's a smooth, continuous curve that's going on the graph. So as long as we can remember or figure out what our quadrantal angles are, then if we just connect those points, then we'll have our smooth, continuous curve. So we know at 0, our sine curve starts at 0, and then at pi over 2, or at 90 degrees, it goes up to 1. And at pi, or 180 degrees, it goes back to 0. Then at 3 pi over 2, it's at -1. And at 2 pi, we go back to 0. So if we connect our curve, and these are not pointy peaks, they're curves, and we put arrows at the end because it continues, we can go back this other way. So if we were to go counterclockwise around our circle, this would go down to -1, up to 0, +1, and back to 0. And then again, we would connect our curve with a smooth, rounded curve and end with an arrow. So that's what our sine curve looks like. And these are some facts about the sine wave, or the sine curve. The graph is continuous over its entire domain. So the domain is the x-axis. The graph is symmetric with respect to the origin, so it's called an odd function. If you remember what that means that if we were to rotate it 180 degrees on the origin, it would look the same. So if you were to flip your paper upside down, that curve is going to look the same as when you started. The x-intercepts, or the roots, are multiples of 180 or pi. So every pi degrees, that's where it's going to touch the x-axis. So here, then at 1 pi, 2 pi, 3 pi, or -pi, -2 pi, all of those are the roots. And the period is 360 degrees, or 2 pi. So a period is the number of degrees or radians that it takes to make one complete curve. So if you'll notice, we start at 0, we go up to 1, 0, -1, back to 1, and it just starts over. So that would continue to infinity, because the domain is from -infinity to +infinity, and the range is from -1 to +1. So that's how high and how low the parent function of the sine curve goes. Now, let's look at cosine. If you'll remember, cosine is x over r, and of course, in the unit circle, since our radius is 1, again, it would just be the x values. So I'm going to mark up our graph with the same values on the x and y axis as we had on the sine curve. Alright, so now we have the same values as we did on the sine curve, and if you'll remember, the x values, when we go on our unit circle, for 0, when we're at 0 degrees or 0 radians, the x value is 1. So our cosine curve is going to start at +1. And then when we get to 90 degrees, or pi over 2, the x value is 0. At pi, or 180 degrees, the x value is -1. And at 3 pi over 2, or 270 degrees, our x value is 0 again. And then at 2 pi, it goes back to 1. So this is what our cosine curve looks like. And then, of course, it continues if we go on the negative values. And again, if we connect them, we have a smooth, continuous curve. And of course, we need arrows again at the end because it continues, it's continuous. So some facts about the cosine wave or curve is that it's continuous over its entire domain. The graph is symmetrical with respect to the y-axis, so it's an even function. If you'll remember what that means, if we were to fold it on the y-axis, then it would be symmetrical. The x-intercepts, or the roots, are in the form of 90 times 2 pi plus 1, or pi over 2 times 2n plus 1. So it starts at pi over 2, and then we add pi to that, and that's where all of the roots would be. The period is 360 degrees, or 2 pi, so it takes 360 degrees for one complete cycle. The domain is from negative infinity to positive infinity, and the range is from -1 to +1. If you'll remember, that's the same as the sine function. Now, the graphs of all trig functions can be changed by stretching or compressing either vertically, horizontally, or both. Every number in the equation explains a transformation of the original parent graph. The parts of the trigonometric function graph are given in the equation in this form: y is equal to a sine of bx, or y is equal to a cosine of bx. Now, we're going to add some more to it a little later, but we're just starting out with a few modifications to the graph. So if our graph looks like this, a represents the amplitude of the graph, and the amplitude is just the height of the curve. So it means the maximum or the minimum. So the peaks and the valleys of the curves, that's what the amplitude is. And then B represents the frequency of the graph. The frequency is the number of complete curves that should be drawn. So to graph one complete sine or cosine curve, you need to know the period. The period is how many degrees or radians you need to draw one complete curve. The period, to get the period, use 2 pi over b, because in the sine and the cosine graphs, the complete period is 2 pi, or 360 degrees. All right, so we're going to graph the following over one period. Now, so we had we had y is equal to a sine of bx was the little formula that we were following. Well, there's not a b in this graph. That would be some number multiplied times the x, or the angle. But we do have an a, so that means that our amplitude has changed. Instead of our amplitude being 1, it's 2 here. So let me mark up our graph. I'm going to say that this is 1.5, 1, not 1.5, 1/2, 1, 1.5, and 2. And then these are the negatives, -1 and -2. All right, so the rest of it stays the same. So if you'll remember, our sine graph starts at 0, 0, and then it goes up. When it gets to pi over 2, it goes up to 1. Well, in this case, since this is a 2, instead of going up to 1, it's going to go up to 2. And then it goes back down to 0. Then instead of going down to -1, it's going to go down to -2 and back up to 0. All right, so then we just connect our points. And there we have our graph of y is equal to 2 sine of x. Excuse me. All right, for y is equal to negative cosine of x, this negative is going to reflect our graph over the x-axis. So that's the only thing that's changing in this graph, is that negative sign. So that means the values are all going to be the same. It's just going to be the opposite on our y-axis. So let me mark these up. So if this is 1/2 and this is 1, let me just mark the ones, -1 and +1. Okay. So for cosine, we know that cosine normally starts on +1 at 0. So instead of being at +1, it's going to be at -1. And then it would normally go down to 0. Well, so it's still going to go to 0, it's just going the opposite direction. And then instead of going to -1, it goes to +1, then back to 0, and then -1. All right, so this is what Let me start over. Kind of missed the marks there. All right. Okay, y'all are just going to have to deal with my imperfect drawings here. Sorry about that. Okay, close enough. All right, that's what our cosine or our reflected cosine curve would look like. All right, here we have a little more going on. So this time we do have an A and a B. So let me write out what we have here. So the A tells us what our amplitude is, or how high or low it goes. It's the absolute value of whatever is in front of the trig function. So our amplitude is 4. And then now we need to know what our period is. Okay, so our period is B or 2 pi, our normal period, divided by B. Okay, so this is 2 pi divided by 1/2, which, you know, we can't divide by a fraction. We would have to multiply by the reciprocal. So that means we're going to keep 2 the same, multiply times the reciprocal of 1/2, which is 2. Okay, so that would mean that our period is 4 pi. So instead of everything happening in 2 pi, it's going to happen in 4 pi. So I'm going to need to change these marks on the x-axis. Now, before I change these marks, if you'll notice, every time we graphed the cosine or the sine function, we had 5 marks, but it's 4 sections. Okay, so like this is 1, 2, 3, 4 quarters, 4 key points on our graph. So anytime we're graphing, we need to know where those key points are going to be, where those transition points or roots are. All right, so that's what we're going to need to mark up. So to figure out where those marks need to be, I take my new period, which is 4 pi, and divide it by 4. Whatever your period is, you're going to divide it by 4 to determine what or where each of those marks need to be. So 4 pi divided by 4 would be pi. So that means that our key points are going to be pi distance apart. All right, so my first one is going to start at 0 because that's where it always starts. We haven't shifted or anything, so we start at 0, and then my first key point or quarter is going to be at pi. And then the next one would be at 2 pi, 3 pi, and we're going to end at 4 pi because we said that that would make one complete period of the graph. All right, and then also, since our amplitude is 4, we know that we're going to go up to 4 and down to -4. All right, and we know that cosine normally starts at 1, so it's going to start at the highest point. All right, then at our next key value, we're going to go down to 0. Then the next one, we go down to the lowest point, back up to 0, and then the highest point. And then we connect our values on our graph, and that is our new cosine curve. All right, here's our last graph. We have y is equal to -2/3 sine pi x. So again, let's find what our amplitude and our period is. Our amplitude here, remember amplitude is the absolute value, so it's just the absolute value of how far it is from that x-axis. So it's 2/3 away from the x-axis. And then our period is our regular period, which is 2 pi, divided by b. So it's divided by pi. Those would cancel, and my period is 2. And that's 2 radians is what that stands for. And then we have a reflection over the x-axis. So it's reflected. All right, and now we need to mark up our graph. So on our y-axis, since our amplitude is 2/3, and you can make these spaces whatever you want it to be. So since the amplitude is 2/3, I'm going to say, well, this is 1/3, and this would be 2/3, and then 3/3 or 1. Okay, so negative 1/3, negative 2/3, and negative 1. Okay, and then for our key points, or our quarters, we take what our new period is and divide it by 4. So that means that our first mark is going to be at 1/2, and then we add that every time to get our other mark. So we start at 0, the first mark is at 1/2, 1/2 plus 1/2 is 1, and then we have 1.5, or 3/2, and then we would have 2. And again, those are radians. So now let's plot our graph. Well, we know that sine starts at 0. Okay, so it's going to start at 0, 0. And since it's reflected, instead of going from 0 up, we're going to go from 0 down. All right, so we're going to go to our lowest point, which is negative 2/3 at our first quarter. Then we go back up to 0, and then instead of going down, we're going to go up now to 2/3, and then we go back to 0. And then we connect our points. And that's how we graph the sine and cosine functions and its translations.